Okay, so I think we can start. Today for the astrophysics talk, we have our own Roberto Decarli that is coming from the other side of the building. And he will talk and tell us about quasar-galaxy merger at redshift 6.2 and all the news from JWST. So please, and I will let you know about the 5 minutes.
Yeah, thanks. Welcome. Good afternoon, everybody. Thanks for the organizers for having me. I thought to give an update on this project. This is a project that I have been working on with my postdoc Federica and with Emanuele Paolo Farina from Gemini Observatory and a long list of other collaborators, including Roberto and Andrea, Marco. And it's based on a data set of JWST observations of this quasar-galaxy merger at a high resolution. So just a bit of context, we're talking about the first giga-year of the universe, and this is the timeline, and we know by now some 600, 700 quasars. This is roughly their distribution in terms of cosmic epoch, where we observe them. And this is not a lot of time. The universe doesn't have a lot of time for a lot of astrophysical processes. You can have a rough idea of what I'm talking about if you compare it, for instance, with a typical lifetime, main sequence lifetime of massive stars. And you see that basically, even for the most massive stars, you have time only for a few generations of stars, right? Not many. And that has implications on the kind of metal enrichment you expect in the ASM of higher galaxies. In terms of dynamical time scales, you can typically refer to the orbits of the Sun in the Milky Way, so about 250 mega-year. And that, again, it tells you that a system like the Milky Way would not be dynamically relaxed by redshift 1 just because there's not time enough to do several orbits of the stars inside the system. For reference, if you're thinking large-scale structures, a source that is moving about 1,000 kilometers per second can cover about 1 megaparsec in 1 giga-year. So again, large-scale structure will not be realized, and everything is assembling and forming. And the final time scale that is relevant for this conversation is the salpeter time. This is the e-folding time of a supermassive black hole that is growing at a fixed radiative efficiency, epsilon, and accretion rate. And if you take the typical Sloan quasar, you have an efficiency of 0.1 and accretion rate of 0.1, and that gives you a salpeter time of 450 mega-year. Again, that means that the universe doesn't have a lot of time to grow these black holes. These pictures just to show you that it's very exciting to study these quasars because you really push our understanding of the universe and all these mechanisms from dynamics of galaxies, star formation, growth of black holes to the extremes. Now, ideally, we would like to plug all this information we have in some large-scale cosmological simulation and let your ab initio condition evolve until you form these quasars. This is something that people have been trying to do, and this is a compilation from a paper by Melanie Buzzi and collaborators, where you see the yields of different cosmological simulation. These, in terms of quasar population, these are the color points in the bottom left of this panel in a luminosity versus black hole mass diagram. And you can immediately see when you compare this population with the observed population of quasars that one is in the bottom left, one is the top right, and this disjoint parameter space is the reflection of a number of limitations that numerical methods have. In particular, the fact that quasars are extremely rare. This kind of quasar that we're talking about, we have typically 1 quasar per cubic gigaparsec. So if you want to have several of them in your simulation, you need to simulate a volume of several gigaparsec cubic gigaparsec, which is a pain. And then you need to apply some prescriptions on how to put the seeds of the black hole, how to let them grow, and how they release back their energy to the interstellar medium of the galaxy, so via feedback mechanism. So I would argue that studying these quasars at the moment is still extremely driven. It's a field that is extremely driven by observation rather than our simulation or theoretical approach. So that's why studying real objects is extremely important, and trying to get as much information from observation is really key. So today we'll talk about this system, PJ308-21. It's a quasar observer redshift 6.2. It was originally discovered in the Pan-STAR survey. And in our follow-up with ALMA in C++, we found that the quasar-galaxy is interacting with at least one, possibly two companion galaxies. These are also detected in the rest frame UV emission with HST. And the whole system is embedded in a luminous Lyman alpha halo that we detected with NIRS. So we did an observation with NIRSpec IFU in cycle 1 with JWST. This is the work that Federica has been working on looking at the quasar emission. The red map here is the channel range corresponding to the H alpha of the quasar, and you can immediately recognize the 6 petals shape of the PSF of JWST. And if you extract the spectrum here, basically we can now observe in spectroscopy, extend the spectroscopic coverage of this system beyond the rest frame UV that we had before, thanks to Muse observation here and the X-shooter, all the way to the rest frame optical line. And this was a regime that until now we could only probe with in photometry with Spitzer and Wise, and now you can get a spectrum out of this with JWST. But more excitingly is to look at this, the quality of the spectrum. The signal to noise is booming. We have about 300 in signal to noise per spectral pixel. And you see that this is the typical quasar of a redshift 0, 2 kind of quasar, right? The features are the same, the broad H alpha, Hbeta gamma line. We have the iron emission, the oxygen 3 line. In particular, the analysis that Federica carried out showed that the broad Balmer lines are well described by a single Lorentzian profile. And you see here in the red wing of the Hbeta line, you have this bump here. This is due to blue shifted oxygen 3 emission. And we'll come back to that later on in the presentation. The black hole mass that we infer based on either H alpha or Hbeta is completely consistent with what we had before based on the magnesium line, which is a line that you observe in the rest frame UV, and it's about 2 times 10 to the 9 solar masses. So in all respect, the rest frame optical phenomenology of the quasar appear to be consistent with what we knew for quasar at much lower redshift. Despite, again, we are talking about very early cosmic epochs. But of course, this was IFU observation, so you don't have information only on the central source, but you have also information on the whole system. In this map, we compare the C+ map emission from ALMA in orange with the oxygen 3 line. This is the 5,700 line that you have in the frame optical. And you see that there is a complex structure here. I'm highlighting a few different regions. We have the east companion, the west companion, the quasar-galaxy here in green. And then you have these other 2 regions, sort of a bridge connecting the quasar-galaxy with the west companion, and the outflow that we'll come back to later, but basically you see it's observed in oxygen 3, but not really in C++. We don't have only oxygen 3, we have a whole suite of rest frame optical lines, H alpha, Hbeta, helium, nitrogen, and then again the oxygen 3 line we saw before. The oxygen 3 4363 angstrom is the auroral line, and the sulfur lines. And you can play with these maps and make nice a map with the line ratios. Like in this case, we have the nitrogen over H alpha. This is typically considered as a metallicity indicator and can be used as a probe of AGN activity. And you see from the map, from the color scale, that different regions have different values of this ratio. And the same for the oxygen 3 over Hbeta, which is typically considered as an indicator of how hard is the ionization field. And again, you see very high values here and lower values in the Western companion. If you extract again the spectrum in the different subregions of the system, and you compare with the BPT diagram, so the ratio of these four emission lines, the purple shades here is the typical Sloan galaxy at redshift 0.1. And you see that you have the AGN population here and the star-forming galaxy here. And you see that the host galaxy of the quasar stays where you expect the AGN to be, while most of basically all the other parts of the system are indicative of a star formation kind of photoionization with a shift upwards, pointing to higher ionization conditions, which is not the first time it's observed in basically all the high redshift galaxy surveys with JWST. This was one of the first big surprises that you get a much higher ionization condition. If you plug this into some cloudy model, you can try to infer some physical quantities corresponding to these properties. And in particular for the East and West companion, you see the East companion is down here, basically with the solar luminosity, solar metallicity, sorry, and relatively low ionization conditions, while the Western companion has much higher ionization conditions and lower metallicity. You can then consider the helium over Hbeta. This is an interesting line ratio because helium has a much high, it's a high ionization energy, so you really need hard photons to photoionize it. And as a matter of fact, this is a discriminant between AGN photoionization and star formation conditions. So high photoionization, high helium to Hbeta ratios imply photoionization like from an AGN. And you see that for the outflow and the galaxy of the quasar, we seem to have pretty high values of helium over Hbeta, which makes sense. It's all photoionized by the quasar. While for the West companion, we have very low values, which are suggestive of star formation. This is interesting because a few years ago, a study carried out by Connor and collaborators found that there are number 3 hard X-ray photons associated, especially consistent with the West companion. So there was a claim that this could be an indication of an obscured AGN in the West companion. But this seems to be ruled out by all the photoionization analysis that we carried out with the JWST data. We can also do extinction maps using the Balmer decrement, the Halpha over Hbeta. And here I want to emphasize the comparison between the West companion and the East companion. The West companion seems to be less obscured, and then the East companion is consistent with the fact that the dust map in emission, shown here in contours, seems to suggest there's less dust in the West companion than the East. So at least on a quantitative base, qualitative base, the things seem to make sense. We can make map of metallicity. We saw before the analysis on the integrated spectra from the BPT diagram, but you can actually make maps. And I really cannot emphasize enough that a couple of years ago, I would dream to have a single measurement of the metallicity in a quasar galaxy redshift 6. That was extremely difficult to achieve. And now you don't have just the measurement, you have the full map and in different tracers. So it's really amazing what we can do now with this data. This again, we find different values for the East and the West companion, and high metallicity values for the quasar galaxy. The companion galaxies are detected marginally, but detected in their starlight continuum also, and you get masses of twiddle 10 to the 10, which is much lower than the mass of the Quasar's galaxy, which is twiddle 10 to the 11. But still, they are extremely massive sources. If you compare with the gray points here, which are galaxies from at redshift 6 from a blank field survey with JWST, so it's the uncover survey. And you see that basically we are talking about a really massive end of the distribution. If you compare the star formation versus the stellar mass, you end up pretty much in the regime of the main sequence galaxy, although to be completely fair, the main sequence is not completely well defined at redshift 6, but this is shown by these lines there from two theoretical works. The fact that typical main sequence galaxies also confirmed by the fact that you can place them on a sort of a Schmidt-Kennicut law, the star formation law, where we use the C+ to infer the spatial distribution of gas, so the gas surface density, and then we compare this with the surface density of star formation measured either from the rest frame UV or from the dust or the H-alpha after correcting for extinction. And you see that pretty much we end up in the regime of depletion timescales of order of a giga-year, which is the typical main sequence kind of depletion timescale. I have to comment here that this analysis was only carried out in the extended part of the host galaxy. It's not considering the central 0.3 arc-second, where the quasar is too bright, so we cannot access either the UV or the H-alpha. So it's possible that we have a starburst in the central part of the quasar, but we cannot consistently do the analysis. Of course, we don't have only maps of the emission and the morphology, we also have velocity fields. This beautiful map shows that basically everything that is south and west is blue shifted, and everything else is red shifted. And we can actually play a movie where we go around move around the channels, and what you see here is the oxygen 3 emission. And you see here the emerging of the west companion, the bridge. Here is the west companion, the bridge. And then here you will have the host galaxy of the quasar, the outflow, and the east companion is emerging here. This is, of course, everything after the removal of the quasar point spread function. So if you look a bit more carefully at the channel maps, you will see that the west companion is not actually connected with the bridge, which is what we originally thought. We thought it was a sort of a tidal tail, but it doesn't seem to be the case. It's actually very tempting to look into some emission at this side. So like as if the bridge is actually forming this sort of arc, which passes through the quasar location. This is for the blue channels, and if you go to the red channels, you can basically pretty much play the same game and find a similar structure with the outflows. So you have a north-east arc in the red channels and the southwest arc in the blue channels. So it's very tempting to now I'll play the same movie with the overlaid, and you see here and here this sort of arcs sort of distribution. And it's very tempting to think about this as a sort of biconal outflow, emerging from the quasar location, and then basically what you get in projection is the conical cut of this shape. The outflow is probably tilted with respect to the line of sight with an angle of phi and as an opening angle of theta. And you can play a little with the geometry. So from Federica analysis, we saw there's a broad component of the oxygen 3, that's blue shifted by about 2000 kilometers per second. And then you compute, okay, the velocity here, we can measure it from the blue component of the outflow. We can do the same game on the red component. You get sort of, you play a little with trigonometry, and you get estimates of the angles that, depending on the assumption, go between 35 and 45 degrees, which is what you see in this plot. And because we have a velocity, we have the full extent, it's the order of 9 kiloparsec. So you have an estimate of the minimum time that the quasar was on, right? So in order to push the material all the way to 9 kiloparsec, it has to be on for at least 4 mega years. You can make an estimate of the mass load of the outflow. This starts from the oxygen 3 luminosity, and there's two key parameters as scaling. F1D2 is the fraction of oxygen 3 ions which are in the 1D2 energy level, which is the one from which the 5007 angstrom line originates. And then you need an abundance in order to have a nitrogen mass. Luckily, we have metallicity estimates, so we are not really lurking dark here. And for the F1D2, you can, well, the basic thing you can do is to assume it's local thermal equilibrium. So you have an assumption on density and excitation temperature, and for reasonable number like 10 to the 3 and 10 to the 4 here, you get, I think it was order 10 to the minus 4, and for F, which in the end boils down to this kind of mass for the outflow. So this is about 5 times 10 to the 6 in the east arc and the west arc, and then about 4.5 10 to the 8 for the component on the line of sight. So the dynamical mass of those galaxies is 2 times 10 to the 11. The velocity is, the escape velocity computed at 1 kiloparsec is about 1300 kilometers per second. It's less than the 2000 we mentioned, right? So the outflow material is not bound to the galaxy. It will not fall back in this rough cartoon, right? On the other hand, this has a minimal impact on the life of the galaxy because the mass that is displaced is tiny. It's basically less than 1% of the total gas mass of those galaxies. Just to conclude, when you have a biconal outflow with this sort of arrangement, it's very tempting to see a connection between this direction of this red component of the outflow and the giant Lyman alpha halo you have on the east side of the quasar. So it's tempting to say that at least part of the gas was placed there by the outflow. Having this as a quantitative bulletproof argument is extremely difficult, though. So one thing we tried to do was to extract again the oxygen 3 map and the H-alpha map using exactly the same wavelength range, where you observed the same velocity range from which we observed the Lyman alpha emission. This produced this noisy map that you see in blue. It's the Lyman alpha, but the green and red are the oxygen 3 and H-alpha. And basically what I want you to get away to take from this map is that there's pretty much no H-alpha except here where basically you start to see the east companion, and there's pretty much no oxygen 3 except for this plume that we have been talking about for quite some time now. You can actually compute the ratio between Lyman alpha and H-alpha. In this case, we average it over different annuli and sectors of the halo just to have a better signal to noise. And you see that basically pretty much everywhere in the halo, we end up with values of several hundred in Lyman alpha over H-alpha. This is interesting because if the halo was powered by recombination, you would expect a ratio that is about 9. if there is dust in the CGM, you lower this ratio because you absorb Lyman alpha photons before the Halpha. And if you have high ratios, that's suggestive of fluorescence because Lyman alpha is fluorescent and the Halpha is not really. And we are pretty much in this regime. So we have an indication of which kind of mechanism is powering the Lyman alpha emission. So I wrap up. We learn a lot about the quasar galaxy. The black hole is 2 times 10 to the 9. The solar system is extremely matter rich. There's photoionization conditions throughout the host galaxy, and the dynamical mass is in the 10 to the 11, so an extremely massive source for the high redshift universe. We looked at the quasar companions. We have 2 galaxies with very distinct properties, but both of them have 10 to the 10 solar mass and stellar mass, and they are clearly dominated by star formation condition in the photoionization budget. And we start to explore the origin and the powering mechanism of the error. And with this, I wrap.
Questions, please.
Roberto, definitely mine should be a stupid question since I'm not familiar with such a high redshift. But how can you decide that you have a quasar and 2 companions, and in particular, that was the bridge at resistance and then an outflow? I mean,
yes. So, sorry, just the video. Let me get.
When you say companions, you mean
so
galaxy?
You see starlight emission.
With the same redshift.
Yes, yes, yes. So the fact that you see emission lines for all these components, so you have no ambiguity that these are actually at the ratios of the quasar. Yes. And you see starlight emission. Yeah, so you see starlight emission, so you know that has to be galaxy kind. It could be part of the host galaxy of the quasar, but the dynamic don't really match. So the host galaxy, in this case, with the oxygen 3 line, is not super obvious, but you already see it's kind of edge-on disk, which is rotating this direction. This component is completely redwards. It's redshifted.
I see 2 peaks in this companion, so
it's so yeah. In the original the 2019 paper we did on this source based only on the C+ observations, we were arguing whether it all could be part of a single galaxy that was strict. The fact that we get very different metallicities and very different photoionization conditions suggests that there are 2 different galaxies. But I mean, getting to that level of information, it's hard, right?
And they are consistent with being gravitationally bound?
Yes, 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 yes. And the fact is you have 2 times 10 to the 11 galaxy.
Yeah, sure, it's big.
Yes, it's big, it's very big. On the outflow, it's very difficult to say if this component is actually a tidal tail or not. What suggested the outflow hypothesis was the fact that this is symmetrical to this one, and that this is actually bluer than the west companion. And if you look at the single channels, it seems like they are not they're close, but they're not really touching. You know, it's not, this one is not really departing. So it's tempting to think it's an outflow, but it's
Question.
Okay. All right.
I don't know.
Okay. But just some curiosity related to the mass estimates of the quasar-host and the outflow.
yes,
The mass of the outflow. So quasar-host.
it's dynamical,
Dynamic.
but based on C++, yes.
Just dynamic, and the outflow did you assume a geometry of the outflow? The formula you
No, in that case, the formula I was given was just the integrated luminosity and then converted into a mass. Yes, but
so you have all done all
the thing is, because it's an outflow component, you can't really rely on a dynamical argument, right? You cannot. It's not virialized, right? So you cannot compute it from the geometry per se.
Yes, but you have the geometry.
Yeah, but that's extremely speculative. I mean, I agree with Angela that you can't really tell, right? So.
Yes, so the geometry and the numbers for the outflow were derived from JWST data alone, right?
Yes, yes, 100%.
So is it the line of sight crossing some part of the outflow, the blue shift part?
So you have to, on the quasar spectrum, you see this blue shifted component in oxygen 3, right?
Yes.
I'm assuming that's the actual velocity of the outflow. So without the projection, because it's pointing in your direction by construction.
I was wondering whether in the UV part, like carbon plus carbon 4
Yes.
Absorption on the UV rest frame spectrum, there's a sign of outflow that are consistent with.
I think so. We looked into the spectrum. There are a number of Lyman alpha absorption features in the Msun spectrum. Some of them might be consistent with the profile of the 2000 kilometers per second. I think so we see some absorption feature corresponding to C4, but I don't think they were matching velocity. It's clearly a complicated system, so it might be that what you see is a different component, but I don't think that the C4 part was traced in at 2000 kilometers. The Lyman alpha you see, because the Lyman alpha has a slow, I mean, there's the Gunn-Peterson effect, but the bubble photoionized by the quasar is big, so you do see absorption even in the blue side of the Lyman alpha. And there is a prominent absorption at 2000 kilometers per second, so things make sense, at least on a qualitative.
So from the C+ modeling, are the data good enough to estimate an angle of the host?
For the host, it's pretty much a job. It's if there is an angle, it must be below 30. I mean, with respect to the perfect Liaison's case. It's a bit hard to because it's a complex system, right? You have to mask out the companions and the more diffuse emission, and the way you do it will change your, the significance of the smaller inclination angle. But it's pretty much a job.
Okay, we have time for the last question.
Is it unusual to find solar metallicity galaxy at that question?
It is unusual in the broad sense of the galaxy population you see. The results from the JWST campaigns from deep fields point to typically 2.3, 0.2 metallicity. This is a 10 to the 11 solar mass galaxy. So if you think in terms of extremely massive sources, that's probably not so surprising.
10 to the 10. No, the west component.
Yes, okay, but still we're on the massive side, right? Of the galaxy population. So it might be that the environment has been enriched by the quasar, or in general, no. It's you would expect lower metallicities, and that's what deep field search is fine, but maybe this is not the most representative environment.
Okay, I don't see any other question from the chat. No. Okay, so let's